Hello, AP Chemistry students. This is video number 2, and this is the part that we skipped when we were doing video 1. So I'm not sure what page number this is, but it's part 2. And basically what we're going to talk about is we've already talked about how energy travels in waves and this wave-like property. Then we've talked about how matter actually has wave-like property as well. So now we're going to go back to the most important part, which is that energy, anything from the electromagnetic spectrum, can actually have particle-like behavior, can behave like matter. So this is pretty big stuff. All right, so atoms and molecules can only emit or absorb energy in fixed amounts, which we are going to call quanta right here, or photons is a much more common word, okay? This is part of Einstein's work as well. So according to Einstein, basically you can look at energy or electromagnetic radiation two different ways. So when you're in your bedroom and you turn on the light energy fills up the room, right? It's like a beam of light. So that's like our wave-like behavior. Where is the light? Well, it fills up the room. It's like everywhere, right? So we can look at light as sort of this beam of energy that has wave-like properties. But you can also think of that same beam of light as being a stream of particles, like these dots right here. Each one of these particles is a photon of a particular wavelength and frequency. Okay, so let's do some math with this. All right, we can calculate the energy contained in each one of these little quanta or photons. Okay, and here's the formula. The energy of a photon is basically represented by Planck's constant, right here, times the frequency. And the basic premise is that Planck's constant is sort of the smallest base unit of energy. And that constant never changes, 6.63 times 10 to the negative 34th, and the units are joules times seconds. Right? But as you increase the frequency, then you're going to increase the energy of that particular photon. Now, this particular formula is the exact same thing. It's just instead of using frequency, they just solved for frequency in terms of wavelength. Okay, so they just basically brought in this formula right here that we talked about the other day and just substituted it in. So it's your preference. I'm almost 99% certain that this is the one that's on your AP chemistry equation sheet. But the basic relationship is real simple. As frequency increases, of course, that's going to be a more energetic photon, and then it's going to be a shorter wavelength. So this is low energy photon, and this would be, ooh, that's a nice wave. Woo! That would be a higher energy photon. All right, so let's just do some practice with this. So when you get to these particular examples, question 2, A, B, C, I would suggest you work through these, okay? So pause the video and then resume and just check your answers, okay? So I'm assuming that you paused. You've completed these. Did you? Did you? All right. So this first one says, well, let's go to this page. The frequency of the electromagnetic radiation produced from a sodium vapor light. And by the way, sodium vapor lights, hello. Like when you're driving down the road and you see like a street lamp and it has sort of that nice yellowy glow, that probably is a sodium vapor light. Okay, very common what we see around here. So let's say it has a frequency that's given here, 5.09 times 10 to the 14th. Okay, so calculate the wavelength. Well, that's nothing new. So we'll use the relationship with the speed of light. And you guys can solve. My only reminder here is that you got to pay attention to the units. So it's the speed of light over that frequency. The seconds cross out. Your units will be spit out in meters. That's the standard unit of representing a wavelength. But this particular question said to express that in nanometers. Okay, so there's 1.0 times 10 to the ninth. Well, yeah, you could do it this way. 1.0 times 10 to the negative ninth of a meter equals 1 nanometer. If you don't like it that way, now that I think about it, that's probably not how I would have done it, even though I did this problem. I probably would have gone 1 meter equals 1.0 times 10 to the ninth nanometers, meaning there's like a lot of little tiny, tiny, tiny nanometers in 1 meter. But whichever, however, it doesn't matter. You come up with 590, okay? And if you remember correctly, if we just whoop, whoop, go back a little bit here, I remember that visible spectrum, you kind of got to know these ranges. Okay, so violet's like in the 350 nano region, so that's a real short wave, all the way to red, which is your long wave low energy, about like 750 thereabouts. Okay, so if we're talking about 550, is that what I said? That might fall here in the yellow range someplace. Okay, wonderful. So that's easy. And then it says calculate the energy in joules of a photon, a single photon, emitted by this excited sodium atom, the sodium vapor light. Okay, so now we're going to solve for the energy of a photon. So there's Planck's constant, and we multiply it by the frequency, and easy enough, we're done. Okay, so in one photon, there's 3.37 times 10 to the 19th joules. Okay, and your answer, as long as you're using Planck's constant, your answer will always produce that answer in joules. All right, but here's my favorite question, because how often are you usually talking about a single photon? Not usually the case. So this is real common. Calculate the energy of a mole of such photons. So then you simply take that number that you just calculated for one photon and multiply it by 6.02 times 10 to the 23rd. Woo! It's always fun when you get to use a mole. Okay, so the photons cancel out. That would be the total energy of a mole of those photons. And of course, it would be totally natural to convert that to kJs. All right, so pretty easy stuff, just a little bit of plug and chug. All right, but I think what's a little bit more challenging is on the next page is sort of the application or the concepts behind, like, why would you care about thinking about light like a beam of energy versus the stream of particles? Okay, so back to Einstein. This was actually his most important work. This is 100% why he received a Nobel Prize, even though he did so many other amazing things as well. But these were the experiments he was doing. So way back when people were trying to figure out what light really was and what it was all about, he conducted this experiment. Okay, so this is a really simplistic version of it, and in class, we actually, together went through a more difficult version of this. Okay, hopefully you guys know what I'm talking about. But anyway, so it says basically the photoelectric effect is when you take different frequencies of light and you shine it at some kind of metal surface. In this case, this is a sodium metal surface. And basically, if the photons have enough energy, they're able to eject electrons off of that surface of the metal because metals, it is their nature to lose electrons. So here's what we're looking at. In this particular example, the light that we're using here is of the violet wavelength or violet frequency. Okay. And then for this one, it's red light. Okay. So let's just answer the questions together. And if you want to, I would highly suggest you should go through and give these a try and then come back and we can talk about it. So it says, what would happen if you increase the intensity of red light? So intensity is basically how many photons you're shooting at the plate, okay? And the truth of it is if you increase intensity of red light, you know what? Each one of these photons in the red light, doesn't matter how many you shoot at it, not a single one of those photons have enough energy to eject electron. So the answer here is, could you eject some electrons? No, okay? Each photon of red light is not energetic enough. Energetic enough. Okay? So red's not going to work. Even if you increase the intensity, doesn't matter. Now, what would happen if you increase the intensity of violet light? So right now, it's what I want you to take away from this is it's sort of like one photon can eject one electron. So if you increase the intensity of the violet light, well, you know what? That just means you're shooting all that much more additional photons at that plate. So every additional photon you send, that's one more electron. That's one more electron. That's one more electron. So if you increase the intensity of violet light, would you eject more electrons? Yes. More photons equals more electrons. But those photons have to be of some minimum energy. Okay? And then it says, what would happen if you increase the frequency of light? So instead of violet light, let's say you use UV light, which is more energetic. Same intensity. Would you eject more electrons? It's a really, really good question. The answer is no, because if the intensity is the same number of photons means you're going to eject the same number of electrons. Same number of photons equals same number of electrons. So you would eject the same number of electrons if indeed you're using the same intensity. But what would be left over? So what they're getting at is that, you know what? If you're using a more energetic photon, you're going to be able to eject the electron, but it's kind of like bursting a bubble. You know what? You're going to use what energy you need to eject the electron, but what do you do with the extra what do you do with the extra energy? I like to say that that's just going to propel the electron off with more vigor or more enthusiasm, or how that really translates is that that electron will be ejected with more kinetic energy, with more speed. Okay, and in class we went into a little more depth, and that could be measured with